Right now, in this very moment, as you look at the screen, an invisible and completely silent reality is holding your body in space. You don't feel its pressure, you don't see its action, but without it, you would instantly find yourself in free fall, without even realizing what had happened. This force has no smell, no color, no temperature. It cannot be shielded, switched off, or weakened. It penetrates every cell of your body, every atom, every particle, and acts equally on everything that exists. We call it gravity. It is the most familiar and, at the same time, the most mysterious phenomenon in all of physics. Every child knows, if you let go of an object, it will fall down. It is so obvious that it seems almost pointless to ask, why? We build cities, launch satellites, calculate planetary orbits and trajectories of interplanetary missions relying on gravity as a reliable, time-tested tool. Modern navigation systems account for gravitational effects with accuracy down to billionths of a second. Astronomers predict the motions of galaxies billions of years into the future. Engineers calculate the landing of spacecraft on other planets with meter-level precision. And yet, behind this precision lies a frightening fact. We still don't know what gravity really is. Not in a metaphorical sense, but in a strict scientific one. We know how it behaves. We can describe it with equations. We can measure its influence with phenomenal accuracy. But when a physicist asks the most fundamental question, what exactly is the carrier of gravity? Why does mass attract mass at all? What exactly is being curved and why? Science is forced to honestly admit there is no definitive answer. This is not a gap in a textbook. This is not a temporary inaccuracy. This is a fundamental crack in our understanding of reality. Imagine an impossible observation. Imagine that you could switch off all the forces in the universe except one. No electromagnetism, no nuclear interactions, no light, no atoms, no molecules, no chemistry. Almost nothing remains. And yet, the universe does not disappear. It continues to exist as a curved dynamic geometry. Space still knows where matter should be. Time still flows differently in different places. The reason for this is gravity. And here is the paradox. Gravity is the weakest of all fundamental forces, but it is the one that governs the fate of the universe as a whole. Electromagnetism is trillions of times stronger. Nuclear forces hold atomic nuclei together. But only gravity can gather stars, form galaxies, and determine the future of the cosmos on scales of billions of years. Why? Why is the weakest force the most important? There is an experiment that cannot be performed directly, but which is constantly happening around us. Clocks. Two absolutely identical atomic clocks. One at the foot of a mountain, the other at its summit. Time passes. When the clocks are compared again, they show different times. The clock at the top runs faster. The difference is minuscule, nanoseconds, but it is real, measurable, and repeatable. And it means something disturbing. Time flows at different rates depending on gravity. This is not an effect of speed, not an instrument error, not a measurement glitch. This is a fundamental property of reality. Gravity affects not only the motion of bodies, it interferes with the very structure of time. The comment from experts in general relativity sounds almost eerily calm. Gravity does not simply act in space and time, it determines what space and time are. But if that is the case, then a question arises that cannot be avoided. What exactly are we measuring when we measure gravity? The history of science knows many examples where a successful theory turned out to be only an approximation, where perfectly working formulas concealed a deeper and stranger reality. But gravity is a special case. It is the only force of nature that acts on everything without exception, cannot be shielded, has no negative counterpart, and refuses to fit into the quantum picture of the world. Physicists honestly admit, if gravity had been discovered today rather than in the 17th century, it would be considered an anomaly requiring a radical overhaul of the entire theoretical framework. Why? Because in modern understanding, All forces must be quantum. They must be transmitted by carrier particles. They must obey the probabilistic laws of the microworld. Gravity does not. It behaves like a smooth, continuous field, like geometry, like something that doesn't fit into quantum reality. This is not a philosophical problem. This is a practical deadlock in modern physics. Now, imagine another impossible scenario. Take the most accurate theory humanity created to describe the universe as a whole. A theory confirmed by hundreds of experiments. A theory without which GPS, satellites, astrophysics, and cosmology would not work. That is general relativity. Now take the second most accurate theory, quantum mechanics. The theory that describes the world of elementary particles with accuracy unparalleled in the history of science. Both theories work. Both are experimentally confirmed. Both are considered fundamental. And yet, they completely contradict each other when it comes to gravity. Not partially, not in details, but conceptually. One says reality is continuous. The other, reality is discrete. One asserts that space and time are dynamic. The other requires a fixed background. One describes the universe as smooth geometry, the other as a quantum foam of probabilities. And it is gravity that lies at the point of conflict. The comment from fundamental physics experts is starkly blunt. If two of the most successful theories are incompatible, then at least one of them is incomplete, and possibly both. This means something far more alarming than just we don't know something. It means that our current understanding of reality is fundamentally incomplete. But what makes the situation truly frightening is this. All our observations of the universe, from the Big Bang to black holes, are filtered through the lens of gravity. We interpret data relying on a theory that itself may be only an approximation. When we say the universe is expanding, we trust gravity. When we talk about dark matter, we see it only through gravitational effects. When we talk about the beginning of time, we extrapolate gravitational equations into a regime where they stop working. We build cosmology on a foundation that may be cracked. And this is not a hypothesis. This is an acknowledged fact of modern science. That is why gravity is not just another topic in physics. It is the center. It is the point where all roads converge. It is the place where familiar explanations end and questions for which there are no ready answers. Today, we will embark on a journey through the evidence that challenges everything we thought we knew about gravity. We will start with the simple, with the falling apple. We will pass through planetary orbits and curved time. We will peer into black holes and the quantum foam of space. And we will approach the boundary where physics stops giving confident answers. And in the end, we will ask the most dangerous question of all. What if gravity is not a force at all? What if it is a side effect of something much deeper? And what if reality is arranged entirely differently from how we are used to thinking? Get ready. We begin. Long before gravity became an equation, a field, or a curvature of space-time, it was a question of instinct. Objects fall, stones drop, rain descends, fire rises. To the ancient human mind, this was not physics, it was order. The universe appeared to have a natural hierarchy. Heavy things belonged below, light things above. Earth at the center, sky overhead. The cosmos arranged like a layered structure, stable and eternal. This intuitive picture dominated human thinking for nearly 2,000 years. In the 4th century BCE, Aristotle provided what would become the first systematic explanation of gravity, though he never used the word itself. According to Aristotle, every object possessed a natural place. Earth and water sought the center of the universe. Air and fire sought the heavens. Motion, in this view, was not caused by forces, but by purpose. A stone fell because it desired to be where it belonged. It was a comforting idea, elegant, philosophically satisfying, and completely wrong. But its power lay not in accuracy, it lay in how well it matched everyday experience. For centuries, no experiment seriously challenged it. No one questioned why objects fell at the same rate. No one measured trajectories with precision. Nature, it seemed, required no deeper explanation. And then, slowly, cracks appeared. By the late Renaissance, Europe was changing. Precision instruments emerged. Time could be measured. Distances could be quantified. Observation began to replace authority. One of the first to notice something unsettling was Galileo Galilei. Legend tells us he climbed the Leaning Tower of Pisa and dropped objects of different masses. Whether the story is literal or not, the result is real. Objects fall at the same rate regardless of mass, ignoring air resistance. This single observation shattered Aristotle's worldview. If heavier objects do not fall faster, then weight alone cannot explain motion. Something deeper must be at work. Galileo went further. He rolled balls down inclined planes, slowing gravity just enough to measure it. What he found was astonishing. Falling motion followed precise mathematical rules. Distance increased with the square of time. Nature, it seemed, spoke the language of mathematics. But Galileo still could not answer the central question: what causes falling in the first place? He described motion brilliantly. He measured acceleration precisely, but gravity itself remained a mystery. The cause was hidden. That cause would not be named until the late 17th century. In 1666, during a plague-induced isolation in the English countryside, a young Isaac Newton began thinking about a simple question: why does the moon not fall? The moon, after all, is constantly accelerating toward Earth. If it weren't, it would move in a straight line and drift away. Something pulls it inward, yet it never crashes. It perpetually misses the Earth. Newton's insight was radical. The same phenomenon that makes an apple fall also governs the motion of the moon. This was unprecedented. For the first time in history, the heavens and the earth were unified under a single principle. No separate laws for celestial and terrestrial realms. One universe, one rule. Newton proposed a daring idea. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. Mathematically simple, conceptually explosive. Suddenly, gravity became universal. It did not require contact. It acted instantaneously across empty space. It reached from Earth to the stars, and it worked. With this single law, Newton explained planetary orbits, tides, falling objects, and the motion of comets. Predictions matched observations with astonishing accuracy. For the first time, the universe appeared predictable, deterministic. Understand the present, calculate the future. But buried within Newton's triumph was a problem so disturbing that even he could not ignore it: action at a distance. How does one object influence another without touching it? No medium, no signal, no delay. Gravity in Newton's formulation acted instantaneously across infinite distances. Newton himself was deeply uncomfortable with this implication. In private letters, he admitted he found the idea philosophically unacceptable. He refused to speculate on the mechanism behind gravity, famously stating, "I frame no hypotheses." This was not humility, it was caution. Newton knew that while his equations worked perfectly, they explained nothing about the underlying cause. Gravity, in his theory, was a force with no origin. And yet, because the predictions were so precise, the question was quietly set aside. For over 2 centuries. By the late 19th century, gravity became the backbone of science and engineering. It guided cannon fire, it shaped architecture, it allowed accurate navigation across oceans. Later, it enabled the discovery of new planets through orbital anomalies. When Uranus deviated slightly from its predicted path, astronomers did not doubt Newton. They searched for another planet. They found Neptune. This success elevated Newtonian gravity to near mythical status. It was not merely correct, it was trusted. But physics has a pattern. When a theory works too well, we stop asking what it means. And slowly, unnoticed at first, anomalies accumulated. By the late 19th century, astronomers noticed something odd about Mercury. Its orbit precessed. Its closest point to the Sun shifted slightly with each revolution. Most of this motion could be explained by gravitational interactions with other planets. Not all of it. A tiny discrepancy remained. Small, persistent, unexplained. Physicists tried everything. They proposed unseen planets, modified parameters, measurement errors. Nothing worked. Newton's law was nearly perfect, but not quite. At the same time, another revolution was unfolding. Electricity and magnetism, once thought separate, were unified by James Clerk Maxwell into a single field theory. Light emerged as an electromagnetic wave. Forces were no longer mysterious pulls, they were fields permeating space. This raised an uncomfortable question. Why is gravity different? Why does it not propagate as a wave? Why does it not have a field carrier like light? Why does it act instantaneously? Newtonian gravity suddenly felt outdated, incomplete. Then came Albert Einstein. Einstein approached gravity from an entirely different angle. He did not begin with force, he began with equivalence. Imagine falling freely, he proposed. In free fall, you feel weightless. Gravity seems to disappear. Conversely, acceleration can mimic gravity. From this simple observation emerged a revolutionary idea. Gravity is not a force at all. It is a manifestation of curved space-time. Mass and energy distort the geometry of space and time. Objects follow the straightest possible paths through this distorted geometry. What we perceive as gravitational attraction is simply motion through distorted space-time. This was not intuitive, it was not simple, but it explained what Newton could not. Mercury's orbit, gravitational lensing, time dilation, and, crucially, it eliminated action at a distance. Gravity no longer acted through space, it acted as space. But this triumph came at a cost. Einstein's gravity was smooth, continuous, geometric. Quantum physics emerging at the same time was discrete, probabilistic, chaotic. Two pillars of modern physics rose, incompatible at their foundations, and gravity stood between them, unquantized, unresolved, untamed. The story of gravity, it turns out, is not a story of steady progress. It's a story of deeper questions replacing shallow ones, of certainty giving way to unease. We began with falling stones, we arrived at warped space-time, and still the core question remains unanswered. What is gravity really? In the next part, we will see how Newton's law, despite its success, contains hidden assumptions that quietly shape everything we think we know about motion, mass, and reality itself, and why those assumptions may no longer be safe. By the early 18th century, Isaac Newton's law of universal gravitation had done something no theory had ever done before. It did not merely explain observations, it dominated reality. With a single equation, physicists could calculate the motion of planets decades into the future. Astronomers could reconstruct celestial events from centuries in the past. Engineers could predict trajectories, stresses, and orbits with a reliability that felt almost supernatural. For the first time in history, the universe appeared not just understandable, but calculable. And this was precisely the danger, because when a theory works too well, it becomes invisible. Its assumptions fade into the background. Its limitations are forgotten. Its metaphysical implications are no longer questioned. Newtonian gravity did not just describe motion, it quietly redefined what scientists believed reality was. At the heart of Newton's theory lay a radical claim, one so familiar today that it rarely feels radical at all. Space and time are absolute. Space exists independently of what occupies it. Time flows uniformly, the same everywhere for everyone. Within this fixed cosmic stage, matter moves, forces act, causes produce effects. Gravity, in this picture, is a force that reaches across space, instantaneously influencing objects regardless of distance. The sun pulls the earth pulls the moon. Every particle pulls every other particle. This worldview was so successful that it became unquestionable. And yet, embedded within it were assumptions that no one could directly test. What is space if nothing occupies it? What is time if nothing changes? How does a force act without a medium? These were not experimental questions, they were philosophical ones. And physics, intoxicated with success, chose not to ask them. For more than 2 centuries, Newton's law reigned supreme. It guided the Industrial Revolution. It enabled the rise of mechanical engineering. It allowed astronomers to map the solar system with extraordinary precision. Even when anomalies appeared, scientists did not doubt the law itself. They searched for hidden causes. When Uranus deviated from its predicted orbit, no one questioned gravity. Instead, they calculated where an unseen planet must be. Neptune was found exactly where Newton's equations predicted. This was not just a success, it was a warning sign, because it taught physicists a dangerous lesson. If observations disagree with theory, the universe must be hiding something, not the theory being wrong. Gravity became sacred. But beneath this confidence lay a conceptual fragility. Newton's gravity explained how much force acts. It did not explain why mass should attract mass. Why should 2 objects separated by empty space influence each other at all? No mechanism, no intermediary, no delay. The force simply existed. Leading thinkers of the era debated this unease quietly. Some proposed invisible particles, others imagined ether-like substances. None of these ideas survived experimental scrutiny. Newton himself avoided the issue entirely. And so, physics moved forward with an unspoken agreement. We will calculate gravity, not explain it. For a time, this compromise seemed harmless. Then, the universe began to grow, not physically, conceptually. As telescopes improved, astronomers discovered stars far beyond the Milky Way. Nebulae resolved into distant galaxies. The cosmos expanded from a clockwork solar system into a vast dynamic structure filled with motion and violence. And gravity, still governed by Newton's law, was now responsible for everything: galaxy formation, star birth, cosmic structure. The more the universe expanded, the more gravity was asked to explain. And slowly, almost imperceptibly, the cracks widened. One of the most subtle but profound problems lay in Newton's assumption of instant action. According to his equations, if the sun were to suddenly disappear, the Earth would immediately stop orbiting and fly off in a straight line. The gravitational influence would vanish instantly. But this violated a principle that was becoming increasingly central to physics. Nothing travels faster than light. When James Clerk Maxwell unified electricity and magnetism, he showed that electromagnetic interactions propagate as waves at a finite speed, the speed of light. No instant influence, no absolute simultaneity. This raised a deeply uncomfortable question. Why should gravity be different? Why should it ignore the fundamental speed limit of the universe? For decades, this contradiction was tolerated because there was no alternative, until someone asked a different kind of question. Albert Einstein did not begin by modifying Newton's equation. He began by questioning its foundation. What if space and time were not absolute? What if simultaneity depended on motion? What if gravity was not a force acting within space, but a property of space itself? This shift in perspective would dismantle Newton's universe piece by piece. But before that revolution could occur, physicists needed to confront something even more disturbing. Newtonian gravity had no place in the emerging quantum world. By the early 20th century, physics had split into two domains. On one side stood classical physics, smooth, deterministic, continuous. On the other stood quantum mechanics, discrete, probabilistic, inherently uncertain. Quantum theory revealed that at small scales, nature does not behave like tiny clockwork machines. Particles exist in superpositions. Outcomes are probabilistic. Measurement itself alters reality. Forces in this new framework arise from the exchange of particles. Photons mediate electromagnetism. Gluons bind quarks. Bosons carry interactions. Everything fits, except gravity. Gravity had no particle, no quantum description, no place in the framework that described all other forces. And this was not merely an omission. Attempts to treat gravity like other forces led to mathematical catastrophes, infinite results, non-renormalizable equations, predictions that made no physical sense. Gravity resisted quantization, stubbornly. This resistance forced physicists to confront a possibility they had long avoided. Perhaps gravity is not a force in the same sense as the others. Perhaps it's not fundamental. Perhaps it's emergent, a large-scale effect of something deeper. This idea would have seemed absurd in Newton's time, but in the 20th century, it became unavoidable. Because Newton's law, for all its precision, relied on assumptions that were no longer defensible. Absolute space, absolute time, instant influence, deterministic motion. Each of these would fall, and gravity would be redefined. Yet, even before Einstein, subtle evidence hinted that Newton's picture was incomplete. Mercury's orbit continued to defy explanation. Time synchronization experiments revealed inconsistencies. The speed of light refused to behave as Newtonian mechanics demanded. These were not dramatic failures, they were whispers, and physics, for a long time, did not listen. In hindsight, the warning signs were everywhere. Newton's gravity worked, but it worked too well within a narrow domain. It seduced generations of scientists into mistaking predictive power for understanding. It told us what happens, it never told us what is happening. And this distinction would soon become impossible to ignore. Because when Einstein finally replaced gravity as a force with gravity as geometry, he dismantled Newton's universe piece by piece. Space would no longer be passive, time would no longer be universal, and gravity would no longer pull, it would bend. In the next part, we will enter the moment when gravity stopped being a force and became something far more unsettling, the shape of reality itself, a transformation so radical that even today, a century later, we are still struggling to understand its consequences. At the beginning of the 20th century, physics stood on the edge of a quiet catastrophe. Nothing was obviously broken. Equations still worked. Predictions still matched experiments. And yet, beneath the surface, the conceptual foundations of reality were eroding. The problem was not gravity alone. It was space and time themselves. For centuries, space had been treated as a passive arena, an empty stage where matter moved and forces acted. Time flowed uniformly, indifferent to motion, mass, or location. This framework felt self-evident because human experience reinforced it. Seconds passed the same way yesterday as they did today. Distances did not change simply because someone moved faster. But nature was quietly disagreeing. The speed of light, measured again and again with increasing precision, refused to behave like an ordinary velocity. No matter how fast the observer moved, light always traveled at the same speed. This was not just strange, it was impossible within Newtonian mechanics. If velocities add, then light should behave differently for different observers. But it didn't. Reality was violating the rules. Most physicists tried to patch the problem. They introduced invisible reference frames, hypothetical substances like the luminiferous ether, ad hoc fixes to preserve the old world view. One man did not. Einstein did something radical. He trusted the data and abandoned the assumptions. In 1905, Einstein published the special theory of relativity. Its consequences were shocking. Time was no longer absolute. Lengths contracted with motion. Simultaneity depended on the observer. Space and time fused into a single structure, space-time. At first, gravity was nowhere in sight, but the seed of its transformation had already been planted. The turning point came from a deceptively simple thought. Imagine you are inside a sealed elevator. If the elevator is at rest on Earth, you feel your weight. If it accelerates upward in deep space, you feel the same force. Locally, without looking outside, there is no experiment you can perform to distinguish gravity from acceleration. This was Einstein's principle of equivalence, and its implications were devastating. If gravity and acceleration are indistinguishable, then gravity cannot be a conventional force. Forces can be transformed away by choosing a different reference frame, but gravity could be eliminated simply by falling. In free fall, gravity disappears. That is not how forces behave. Einstein realized that gravity was not something acting on objects, it was something shaping the paths they follow. To understand this, imagine space-time not as a flat grid, but as a flexible fabric. Place a massive object on it, and the fabric curves. Objects moving nearby do not get pulled. They follow the straightest possible paths through curved geometry. What we call gravitational attraction is simply motion along those paths. This idea was profoundly counterintuitive. There was no force, no pull, no invisible hand, only geometry. Mass tells space-time how to curve. Space-time tells mass how to move. With this single insight, gravity was redefined. In 1915, Einstein completed the general theory of relativity. The equations were dense, non-linear, and intimidating, but their predictions were extraordinary. They explained Mercury's anomalous orbit exactly. They predicted the bending of light near massive objects. They showed that time itself slows in stronger gravitational fields. Gravity was no longer a background phenomenon, it was woven into the fabric of reality. Space could stretch, shrink, twist. Time could dilate, slow, even nearly stop. The universe was no longer static, it was dynamic geometry. When astronomers first tested Einstein's predictions during a solar eclipse in 1919, the results confirmed them. Starlight bent exactly as relativity predicted. Einstein became a global icon overnight. But among physicists, a different emotion dominated: unease. Because general relativity was not just a better theory of gravity, it was a new conception of reality. In Einstein's universe, there was no universal now, no fixed stage, no absolute reference frame. Even empty space was no longer empty. It had structure. It could ripple. And those ripples, gravitational waves, would carry information across the cosmos. But there was a price. General relativity was incompatible with quantum mechanics. Not just difficult to reconcile, fundamentally opposed. Quantum fields fluctuated violently at small scales. Space-time, according to relativity, was smoothed down to arbitrarily small distances. Put them together, and the mathematics collapsed. Infinity appeared everywhere. This conflict was not academic. At the centers of black holes, at the moment of the Big Bang, at the smallest scales of space-time itself. Exactly where gravity becomes strongest, our theories fail. Relativity predicts singularities, points where density becomes infinite and laws of physics break down.
Quantum mechanics refuses to tolerate such infinities. Both theories are extraordinarily successful. Both are experimentally verified. And yet, they cannot both be correct in their current forms. Gravity sits at the fault line. This realization forced physicists to confront an unsettling possibility. Perhaps space-time itself is not fundamental. Perhaps geometry emerges from something deeper. Perhaps gravity is not a primary interaction at all. What if Einstein's curved space-time is only an approximation? What if beneath it, reality is discrete, quantum, and unfamiliar? These questions would define the next century of physics. But before confronting the quantum problem, there was something else Einstein's theory revealed. Something darker. General relativity did not merely allow black holes, it demanded them. Regions where space-time collapses so violently that nothing, not even light, can escape. Places where time slows to a halt relative to the outside universe. Gravity, pushed to its extreme, destroys predictability. And these objects were not mathematical curiosities, they were real. In the next part, we will descend into the most extreme gravitational environments in the universe, black holes, and discover why they are not just cosmic monsters, but clues to the deepest secrets of gravity itself. Because at their cores, all our understanding breaks down.
Black holes are perhaps the most terrifying and awe-inspiring consequences of gravity. They're regions of space-time where Einstein's equations predict that mass has collapsed into an infinitely dense point, a singularity, surrounded by a boundary called the event horizon. Beyond this horizon, the curvature of space-time becomes so extreme that nothing, not even light, can escape. They are not science fiction, they are the universe's most extreme laboratories for studying gravity. The concept of a dark star appeared in the late 18th century when Jean Michel and Pierre-Simon Laplace speculated about bodies so massive that their escape velocity exceeded the speed of light. But in those days, light was still understood through Newtonian mechanics. It was only with Einstein that the true nature of black holes became clear. Gravity in the relativistic framework is no longer a mere pull, it is geometry itself. And when space-time geometry becomes infinitely curved, the concept of a conventional object breaks down. Black holes are therefore the ultimate test of general relativity. Their formation begins with massive stars exhausting their nuclear fuel. As thermal pressure drops, gravity dominates completely, collapsing the star's core into an incredibly dense point. The surrounding layers may be expelled in a supernova explosion, leaving behind a black hole. But the core itself is gone beyond recognition, a singularity where classical physics loses all meaning. Visualize this. Imagine standing near the edge of a massive trampoline. Place a heavy ball in the center and watch as the surface dips dramatically. Now imagine dropping a bowling ball into the same depression, watching it spiral inexorably toward the center. This analogy, while imperfect, gives a glimpse of how mass warps space-time, guiding objects along the curved paths, geodesics, that define their motion. In black holes, this curvature becomes extreme. Geodesics converge to a point of no return. Time itself slows, approaching a standstill as one nears the singularity. One of the most fascinating consequences of black holes is gravitational time dilation. Near a black hole, time passes much more slowly relative to a distant observer. The closer you get to the event horizon, the more extreme the effect. Theoretically, an object falling into a black hole would appear to freeze at the horizon, its image redshifting into invisibility. Yet locally, time feels normal for the infalling observer. Gravity, in this sense, reshapes reality itself, bending both space and time in ways that challenge our most fundamental intuitions. Black holes also produce gravitational lensing, another extraordinary manifestation of curved space-time.
Light passing near a massive object bends along the curves of space-time, producing distortions, multiple images, and arcs when observed from Earth. The effect was first confirmed during the 1919 solar eclipse, validating Einstein's predictions, but near black holes it becomes extreme. Entire regions of the universe behind a black hole can appear warped, duplicated, or stretched into rings known as Einstein rings. Gravity, once again, is no longer a mere force, it is a sculptor of light itself. In recent years, humanity has obtained the first direct images of black holes, most famously the supermassive black hole in the galaxy M87, captured by the Event Horizon Telescope in 2019. For the first time, the dark silhouette against the luminous accretion disk confirmed predictions of general relativity with breathtaking precision. What was once a mathematical curiosity had become observable reality. And yet, even these monumental achievements raise deeper questions. At the core of every black hole is the singularity, a point where density becomes infinite and our current theories of physics cease to be predictive. Classical general relativity cannot describe conditions at or within the singularity. Quantum mechanics, which governs the microcosm, also fails in such extreme regimes. The combination of quantum theory and general relativity near a singularity generates paradoxes, including the infamous information paradox. When matter falls into a black hole, what happens to the information it contains? Quantum theory forbids destruction of information, but classical black hole physics suggests it is irretrievably lost. Reconciling these conflicting predictions remains one of the greatest unsolved problems in theoretical physics. Gravitational waves, ripples in space-time predicted by Einstein, find their ultimate testing ground in black holes. When two black holes merge, they send shock waves traveling at the speed of light, distorting space as they propagate. In 2015, LIGO directly detected these waves for the first time, confirming a century-old prediction. The waves carry information about the masses, spins, and dynamics of black holes, opening an entirely new window into the universe. We are now listening to the cosmos in a language composed entirely of space-time vibrations, the echoes of gravity itself. Yet black holes are not merely extreme laboratories, they are clues to the very nature of reality. They challenge the assumption that space and time are continuous. They suggest that the classical picture of gravity may be incomplete. The singularities hint at a deeper layer of physics, one that might unify gravity with quantum mechanics, resolve the information paradox, and explain the origin of space-time itself. Some speculative theories suggest that black holes might connect to other regions of space-time, wormholes, or even parallel universes, although these ideas remain highly theoretical. What is certain is that black holes are both a triumph and a warning. They validate Einstein's theory at extremes, confirming that gravity is geometry, yet they also expose the limitations of our current understanding. They demonstrate that the smooth, continuous fabric of space-time can be stretched and warped to the point of incomprehensibility. They reveal that the universe has regions where the very laws of physics as we know them break down. And perhaps most profoundly, they force us to confront an uncomfortable truth. The universe is far stranger than our intuition suggests. Gravity, once thought to be a simple pull between masses, is instead a dynamic geometric phenomenon with consequences that challenge our deepest assumptions about space, time, and reality. In the next part, we will explore gravitational waves in greater depth, these subtle, invisible ripples in space-time that allow us to hear the collisions of black holes and neutron stars across billions of light-years, giving us unprecedented access to the hidden dynamics of the cosmos.
For centuries, gravity was silent. We observed its effects through falling objects, planetary motion, and the bending of starlight, but it communicated only indirectly. Then, in a revelation that reshaped our understanding of the cosmos, scientists realized that gravity could speak, not through sound or light, but as ripples in space-time itself. Albert Einstein predicted these ripples in 1916, only a year after completing the general theory of relativity. According to his equations, when massive objects accelerate, they disturb the fabric of space-time, sending waves outward at the speed of light. These gravitational waves are subtle, stretching and compressing space as they pass. Yet, like the faint tremor before an earthquake, they carry profound information about the universe, collisions, mergers, and the dance of the most massive objects ever known. Visualize this. Imagine a perfectly smooth rubber sheet representing space-time. Place two heavy balls on it, two neutron stars or black holes orbiting each other. As they revolve, they create ripples in the sheet, propagating outward. These waves are incredibly faint by the time they reach us, distorting distances smaller than the diameter of a proton. The universe, Einstein suggested, is alive with these gentle vibrations, recording cosmic cataclysms in a language we are only now learning to decode. Detecting them, however, was another challenge entirely. For decades, scientists attempted to measure these minute distortions with extraordinary sensitivity. In the 1960s, Joseph Weber pioneered resonant bar detectors, massive metal cylinders designed to vibrate under the influence of passing gravitational waves. His initial claims of detection were later disputed, but his efforts ignited a field of research that would mature into the most sensitive experiment in human history, the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two observatories, thousands of kilometers apart, using laser interferometry to measure changes in length smaller than 1/1000th the diameter of a proton. When a gravitational wave passes, one arm stretches while the other contracts. The interference pattern of the lasers revealed these minute oscillations, allowing scientists to reconstruct the properties of the source with incredible precision. This is physics at its most audacious, listening to the invisible, measuring the imperceptible, and decoding messages from billions of light years away. Then, in September 2015, LIGO detected the first confirmed gravitational waves originating from a merger of two black holes over 1 billion light-years distant. The signal, a brief ripple in space, carried enough information to determine the masses and spins of the colliding black holes, confirming predictions of general relativity in a regime of unprecedented extremity. Humanity had, for the first time, directly observed the dance of space-time itself. The universe had spoken, and we had finally listened. But these waves reveal more than mere cosmic spectacles. They are a laboratory for fundamental physics. The frequency and amplitude of the waves allow us to test Einstein's equations under conditions of extreme curvature, far beyond what any solar system experiment could provide. They probe gravity at its limits, where theoretical predictions approach breakdown. By comparing observations with models, we can search for deviations that might indicate new physics, hints of quantum gravity, exotic matter, or hidden dimensions. Moreover, gravitational waves illuminate phenomena that were previously invisible. Black holes, by definition, emit no light. Neutron stars, shrouded in extreme density, are opaque, yet their interactions produce space-time vibrations that traverse the universe unimpeded. In this way, gravitational waves serve as a new sense, complementing light and electromagnetic radiation, granting us access to a hidden universe. Consider the implications. We are now witnessing events that occurred billions of years ago, at distances so vast that light from the same events has yet to reach us. Gravitational waves arrive unaffected, unabsorbed by intervening matter, carrying pristine information across cosmic history. They are messengers from the most violent epochs of the cosmos, from the mergers that shape galaxies to the echoes of the universe's earliest moments. The detection of gravitational waves also challenges our understanding of energy and mass. When two black holes merge, a portion of their combined mass is converted directly into gravitational radiation.
In some cases, several solar masses are released in a fraction of a second, making these events the most energetic phenomena in the universe since the Big Bang. This energy is not emitted as light or particles, but as distortions of space-time itself, a profound reminder that gravity is not just a passive influence, but a dynamic, measurable force shaping reality. Gravitational waves are also gateways to testing alternative theories of gravity. Modifications to general relativity proposed to explain dark energy, dark matter, or the quantum nature of spacetime often predict subtle differences in wave propagation. By analyzing the waveform with exquisite precision, scientists can constrain or rule out competing models, gradually approaching the elusive unification of gravity with quantum mechanics. Perhaps most intriguingly, these waves suggest that spacetime is not immutable. It has structure, dynamics, and a voice. The universe is not static. It vibrates, pulses, and resonates with the motion of its most extreme constituents. Gravity, once considered a simple pull between masses, is revealed as the medium through which cosmic information flows, connecting the distant and the near, the past and the present. Yet, gravitational waves also confront us with profound mysteries. What happens to information in a black hole merger? How do quantum effects manifest in these violent interactions? Could the ripples of space-time themselves contain clues about dimensions beyond our perception, about the fundamental nature of reality? These questions hint at the frontier where general relativity and quantum mechanics collide, the place where our deepest assumptions about the universe are challenged. In essence, gravitational waves transform gravity from a silent actor to an active narrator. They tell the story of the universe in a language that transcends light and matter, and they compel us to recognize that the cosmos is far stranger and more dynamic than our intuition ever allowed. In the next part, we will examine where Einstein's theory begins to break down, exploring the paradoxes and limits of general relativity and why even the most precise theory in human history may be incomplete when confronted with the extreme scales of mass, energy, and spacetime.
General relativity is one of the crowning achievements of human thought. It replaced Newton's concept of a force with the astonishing idea that mass and energy curve spacetime, guiding the motion of everything from falling apples to orbiting stars. For over a century, the theory has passed every experimental test: the bending of light, gravitational redshift, the precession of Mercury's orbit, and, more recently, the detection of gravitational waves. Yet, despite this extraordinary success, cracks begin to appear when we push the theory to extremes. The most immediate of these cracks appear in singularities, regions where the curvature of spacetime becomes infinite. Inside black holes, according to Einstein's equations, all matter collapses to a point of zero volume and infinite density. The familiar rules of physics cease to apply. Space and time themselves break down. Mathematical predictions diverge to infinity, and determinism, the principle that the future can be predicted from present conditions, collapses. Physicists refer to these points as singularities, and they are arguably the most unsettling predictions of general relativity. Not because the mathematics fails, mathematics always yields an answer, but because the answer is physically meaningless. Infinity, in this context, signals the end of the theory. It tells us that the classical description of gravity cannot continue to describe reality under extreme conditions. Another challenge arises from the incompatibility with quantum mechanics. While general relativity governs the macroscopic realm, stars, galaxies, black holes, quantum mechanics describes the subatomic world, electrons, photons, quarks. Both theories are supremely successful in their domains. Electromagnetic dynamics predicts phenomena to unprecedented accuracy. General relativity predicts planetary motion, gravitational lensing, and black hole dynamics. Yet, when we attempt to combine the two, the mathematics becomes inconsistent.
Quantizing gravity in the same way we quantize electromagnetism leads to infinite results that cannot be renormalized. The predictions are nonsensical. Nature appears to resist a straightforward unification. Gravity seems to be fundamentally different from the other forces, refusing to submit to the probabilistic framework that so elegantly describes the quantum world. This tension is not hypothetical, it is directly observable in the most extreme environments of the cosmos. Consider the Big Bang, the origin of the universe. According to general relativity, extrapolating backward in time leads to a singularity, a point of infinite density and temperature where space-time itself vanishes. Quantum mechanics, however, suggests that at such scales, uncertainty dominates, and classical trajectories no longer make sense. The two frameworks cannot simultaneously describe these conditions. One or both must be incomplete. Perhaps the most profound paradox arises in the realm of black hole thermodynamics. Classical general relativity predicts that nothing, not even light, can escape a black hole. Information about the matter that falls in appears lost to the universe forever. Quantum mechanics, by contrast, demands that information cannot be destroyed. This tension is formalized in the black hole information paradox. If information is irretrievably lost, the laws of quantum physics are violated. If it is preserved, we require a mechanism that allows information to escape a black hole without violating general relativity. No consensus has yet been reached. Leading theorists from Stephen Hawking to Juan Maldacena continue to propose solutions, but the paradox remains unsolved, symbolizing the deep divide between gravity and quantum theory. Even at larger scales, subtle tensions appear. Observations of galaxies and clusters reveal gravitational behaviors that cannot be explained by visible matter alone. To account for the missing mass, physicists invoke dark matter, a mysterious substance that interacts gravitationally but not electromagnetically. Alternatively, some propose modifications to gravity itself, suggesting that Einstein's equations may need adjustment in regimes far from Earth. These anomalies, while indirect, hint that general relativity might not be universally complete. Further complications arise in considering cosmic expansion and dark energy. Observations show that the universe's expansion is accelerating, a phenomenon attributed to dark energy. Einstein's equations allow for a cosmological constant, an energy density of empty space, but the magnitude required to match observations is extraordinarily small compared to predictions from quantum field theory, off by over 100 orders of magnitude. This discrepancy remains one of the deepest unsolved problems in physics, illustrating that our understanding of gravity, space, and energy is fundamentally incomplete. In extreme conditions, such as merging black holes or neutron stars, general relativity remains accurate within observational limits. But the underlying nature of space-time, mass, and energy under extreme curvature remains elusive. We are left with precise predictive power, but without a complete conceptual understanding. Gravity works, it bends light, it merges black holes, it stretches and compresses space-time. And yet, when asked why, the theory offers no satisfactory answer. These cracks suggest a profound lesson. The universe is stranger than our models imply. Nature does not conform neatly to the equations humans prefer. Instead, the cosmos operates at scales and energies that challenge our intuitions, our mathematics, and our philosophical assumptions. Gravity, elegant and precise, contains hints that there is more beyond general relativity, a deeper theory that has yet to be discovered. Physicists are now exploring candidate frameworks, string theory, loop quantum gravity, emergent spacetime models, and holographic principles. Each attempts to reconcile gravity with quantum mechanics, to describe singularities without infinities, and to explain how spacetime itself might emerge from more fundamental entities. None are complete, but each offers glimpses of a possible future where the mysteries of gravity may be fully understood. The cracks in Einstein's theory, subtle as they are, define the frontier of modern physics. They remind us that even the most beautiful, experimentally verified theory is provisional, that even the elegant curvature of space-time may conceal deeper truths, that gravity, the force that shaped the cosmos, may also be the key to unlocking its ultimate secrets. In the next part, we will examine the quantum problem, why gravity resists quantization, what it reveals about the universe at its smallest scales, and why reconciling it with quantum mechanics remains the most formidable challenge in all of physics.
Gravity is the oldest and most familiar force in our experience. We feel it every day, keeping our feet planted on Earth, guiding the moon's orbit, holding galaxies together. Yet, when we examine the universe at its smallest scales, gravity becomes the most elusive, the most resistant to understanding, and arguably the most profound puzzle in modern physics. The problem begins with the scale mismatch. Quantum mechanics governs the subatomic world, electrons, quarks, photons, everything that exists in discrete probabilistic units. These particles interact through the electromagnetic, weak and strong forces, each mediated by exchange particles, or bosons. Experiments confirm these interactions to incredible precision. The rules are clean, quantifiable, and remarkably predictive. Gravity, however, refuses to fit into this framework. Attempts to describe it as a quantum force carried by hypothetical particles called gravitons produce equations that explode into infinities when applied at small scales. Calculations become meaningless. No consistent predictive theory emerges. Unlike electromagnetism or the strong force, gravity resists quantization. It remains stubbornly classical, smooth and continuous, even at scales where discreteness dominates the universe. Consider a black hole again, but now on quantum scales. As the black hole shrinks and its mass becomes concentrated, quantum effects should dominate. In principle, the singularity should no longer be infinitely dense, but described by quantum states. Yet general relativity continues to predict an infinite curvature, while quantum mechanics requires a discrete probabilistic description of space and energy. The two frameworks are incompatible. At this junction, the intersection of the very large and the very small, physics breaks down. The tension is not merely academic, it threatens our understanding of causality and information. Classical gravity predicts that information entering a black hole is lost to the universe. Quantum theory insists that information must be preserved. If gravity cannot be quantized, or if the mechanism of information preservation is not understood, one of our most fundamental physical principles is violated. This is not a small inconsistency. It strikes at the heart of determinism and the nature of reality. One approach to resolving this tension is string theory. Instead of treating particles as point-like, string theory models them as one-dimensional vibrating strings. These strings generate all particles, including the graviton, as vibrational modes. In theory, string theory provides a framework in which gravity is naturally quantized and compatible with the other fundamental forces. Moreover, it predicts additional spatial dimensions beyond the familiar three. However, string theory remains largely untested. Its predictions often lie at energies far beyond our current experimental reach, and its mathematical landscape is vast, perhaps even infinite, leading to what some call the landscape problem. While promising, string theory is not yet a completed solution. It suggests that gravity may emerge from a deeper, higher dimensional reality, but the experimental confirmation is still out of reach. Another promising approach is loop quantum gravity, which attempts to quantize space-time itself. In this framework, space-time is not continuous but composed of discrete loops woven into a granular structure, much like a fabric made of individual threads. These loops define the geometry of space and the flow of time, offering a picture of gravity that aligns with quantum principles. Singularities, such as those inside black holes or at the Big Bang, are replaced by finite, well-behaved structures. The infinite density disappears, replaced by a fundamentally quantum geometry. Yet, loop quantum gravity faces its own challenges. While it preserves mathematical consistency, connecting its predictions to observable phenomena remains difficult. Testing these theories requires energies or scales far beyond current technological capabilities. The universe itself becomes both the laboratory and the puzzle. The quantum gravity problem also touches the very origin of the universe. If space-time emerges from quantum rules, then the Big Bang may not have been a singularity. Instead, the universe could have bounced from a prior state or emerged from a quantum fluctuation in a larger multiverse. Time itself may be emergent, not fundamental. Causality, the chain of cause and effect, might be an approximation, valid only in the classical limit of large scales. These ideas are not mere speculation. They are grounded in precise mathematical models that extend Einstein's theory into the quantum domain. They attempt to answer questions that no classical theory can. What is the smallest possible unit of space? How does time behave near a singularity? Can gravity be a force, an emergent phenomenon, or even an illusion? Each answer reshapes our understanding of reality. Experimental hints are beginning to emerge, though slowly. Observations of the cosmic microwave background reveal fluctuations that could carry imprints of quantum gravitational effects. High-energy particle collisions may one day probe extra dimensions predicted by string theory. Gravitational waves themselves, as observed by LIGO and Virgo, may contain subtle deviations from general relativity, offering glimpses of physics beyond Einstein. Each measurement is a step toward testing the limits of our theories. The quantum gravity problem, therefore, is the ultimate frontier. It is where the macroscopic and microscopic universes collide. It is where our most successful theories, general relativity and quantum mechanics, confront each other in stark conflict. It is the place where the universe reveals both its elegance and its impenetrable mysteries. And it leaves humanity with an unsettling realization. Gravity, the force that guides our daily lives, that holds galaxies together, and that warps time itself, may be a shadow of a deeper hidden reality. The gravity we see may be only the surface of an underlying quantum structure, a whisper of a cosmic architecture far beyond our direct perception. In the next part, we will explore dark matter and dark energy, the invisible components of the universe that interact only through gravity, revealing just how much of the cosmos remains hidden and how gravity acts as our only guide in the dark.
When astronomers first mapped the motions of galaxies in the 20th century, they noticed something unsettling. Stars at the edges of galaxies moved far faster than expected. According to Newtonian gravity and even general relativity in the galactic context, the visible matter simply could not generate enough gravitational pull to hold the galaxies together. Without some additional mass, these stars should fly off into the void. Yet, they did not. This invisible mass became known as dark matter. It interacts gravitationally, shaping galaxies, clusters, and the large-scale structure of the universe, but it does not emit, absorb, or reflect light. Essentially, we can see its effects, but not the substance itself. Dark matter constitutes roughly 27% of the universe's total mass energy, vastly more than all the ordinary matter, stars, planets, gas, that we can observe. Gravity is the only force through which we detect it. The evidence for dark matter comes from multiple sources. 1. Galaxy rotation curves. The velocity of stars and galaxies remains nearly constant far from the galactic center, inconsistent with the distribution of visible matter. 2. Gravitational lensing. Light from distant galaxies bends more than expected when passing through clusters, revealing unseen mass. 3. Cosmic microwave background fluctuations.
The patterns in this relic radiation from the Big Bang require more gravitational pull than visible matter alone provides. 4. Large-scale structure formation. The filamentary web of galaxies stretching across billions of light-years requires dark matter to explain its formation and stability. Physicists have proposed numerous candidates: WIMPs, weakly interacting massive particles, axions, sterile neutrinos, and more. Yet, despite decades of searches, deep underground, in particle accelerators, and through astronomical surveys, dark matter has never been directly detected. Its presence is inferred solely through gravity. The universe whispers its secrets, and gravity is the only language in which it speaks. Even more mysterious is dark energy, an entirely different phenomenon revealed in the late 1990s through observations of distant supernovae. Contrary to expectations, the expansion of the universe is not slowing down due to gravity, it is accelerating. The force driving this expansion is called dark energy, a repulsive effect that permeates space itself. Dark energy constitutes roughly 68% of the universe's mass energy, making it the dominant component of reality. Gravity, paradoxically, is both the glue of cosmic structure and the medium through which the universe's expansion is resisted and modulated. Dark energy interacts with gravity indirectly, influencing the curvature of space-time on cosmological scales, yet its nature remains elusive. Is it a cosmological constant, a vacuum energy predicted but inexplicably tiny by quantum theory, or is it a dynamic field that changes over time, as in theories of quintessence? Observations continue to constrain its properties, but fundamental understanding is still out of reach. These discoveries place gravity at the center of the cosmic mystery. It is the only probe we have into the dark sector. Photons, neutrinos, and conventional matter cannot reveal dark matter or dark energy directly. Only gravity, through orbital dynamics, lensing, and cosmic expansion, allows us to infer their presence. Our knowledge of more than 95% of the universe comes entirely from gravitational effects. Gravity, in this sense, is both mundane and extraordinary. It holds our feet on the ground, yet simultaneously informs us about the vast, invisible architecture of the cosmos. It is ordinary in daily life, but cosmic in implication. Observations of the cosmic web, the vast network of galaxies and filaments spanning hundreds of millions of light-years, illustrate gravity's silent orchestration. The filaments, shaped largely by dark matter, connect clusters and superclusters, while voids, immense regions nearly empty of matter, are sculpted by the competition between gravitational attraction and cosmic expansion. Galaxies trace the gravitational contours of an unseen landscape. Every structure in the universe, from the smallest star cluster to the largest supercluster, owes its form to gravity's invisible hand. Yet these discoveries also expose a profound limitation in our understanding. Dark matter and dark energy do not behave as any familiar particle or force. They may obey the same gravitational laws as ordinary matter, but we have no direct insight into their intrinsic nature. Gravity tells us where they are, but not what they are. We measure their effects, not their substance. And the deeper we look, the more incomprehensible the universe appears. Even the cosmic expansion itself highlights gravity's dual nature. Locally, gravity binds galaxies together, forming stars, planets, and life. On the largest scales, it struggles against dark energy, which drives galaxies apart. The same force that allows us to step on solid ground is also a key actor in the evolution of the universe itself. The interplay between dark matter, dark energy, and visible matter raises critical questions. Are our theories of gravity complete on cosmological scales? Could modifications to general relativity explain these phenomena without invoking unknown substances? Is there a deeper theory, a quantum theory of gravity that unifies dark energy, dark matter, and the familiar forces of nature?
Answering these questions requires a combination of astronomical observation, theoretical modeling, and perhaps a revolution in our understanding of physics. Gravity is the thread connecting all cosmic mysteries. Through it, we infer the unseen, probe the unimaginable, and test the limits of human comprehension. In the next part, we will explore the role of gravity in shaping time itself, examining how gravitational time dilation transforms our understanding of simultaneity, aging, and the passage of time across the universe. We will see that gravity is not just a force of attraction, but a shaper of reality itself.
Gravity is more than a force of attraction. According to Einstein's general theory of relativity, it is a sculptor of space-time, bending not only space, but also time itself. The stronger the gravitational field, the slower time flows relative to regions of weaker gravity. This phenomenon, known as gravitational time dilation, is not a theoretical curiosity. It is an experimentally verified reality, reshaping our understanding of how the universe operates. Imagine two identical clocks, one placed at the base of a mountain, the other at its summit. Classical intuition suggests they would tick at the same rate, but experiments reveal otherwise. The clock higher up, further from Earth's gravitational pull, ticks slightly faster than the one below. The difference is tiny but measurable, nanoseconds per day. But it demonstrates that time itself is not universal. Time is local, malleable, and intimately connected to gravity. This effect becomes extreme near massive objects. Near a black hole, time slows dramatically relative to distant observers. A theoretical astronaut hovering near the event horizon would experience seconds, while years pass for someone far away. Gravity reshapes not just the trajectory of matter, but the very flow of time. It forces us to reconsider concepts that we take for granted: simultaneity, causality, and the shared passage of moments across space. Gravitational time dilation has practical implications even on Earth. The Global Positioning System, GPS for instance, relies on a network of satellites orbiting thousands of kilometers above the surface. Each satellite carries atomic clocks, and their timing must account for both special relativistic effects due to their motion and general relativistic effects due to weaker gravity at altitude. Without these corrections, positional errors would accumulate at a rate of kilometers per day. Humanity depends on our understanding of how gravity shapes time. Time dilation also introduces profound philosophical questions. If time flows differently in different gravitational potentials, is there a universal now? Can events be truly simultaneous across vast distances or near extreme masses? Einstein's relativity teaches us that time is not an independent backdrop, but an element interwoven with space and influenced by mass and energy. This interconnectedness becomes even striking when combined with gravitational waves. These ripples in space-time carry not only spatial distortions, but temporal ones. As a wave passes, it stretches and compresses both space and time. Gravity, in its dynamic form, does not merely act, it communicates. It transports information across billions of light years, subtly modifying the very clocks that measure it. One consequence of these insights is the realization that our intuition about aging, causality, and the sequence of events is limited. Near a neutron star or in the vicinity of merging black holes, time dilation can stretch the subjective duration of events to extremes. Observers in different regions of spacetime may witness the same cosmic phenomena in drastically different sequences. Gravity thus introduces a profound relativity to experience itself. Consider a hypothetical spacecraft falling into a black hole. To a distant observer, the spacecraft appears to slow, asymptotically approaching the event horizon but never crossing it. To the astronaut inside, however, the journey is completed in finite time, with all physical processes unfolding normally. This divergence illustrates that gravity does not merely influence motion, it defines the very rhythm of reality, separating perception from universal absolutes.
Even our understanding of the early universe is shaped by gravitational time dilation. In regions of extreme density and curvature, such as near the singularity of the Big Bang, the flow of time becomes ambiguous. Classical physics predicts an infinitely dense origin where time loses its conventional meaning. Quantum gravitational effects may modify this picture, introducing a discrete or probabilistic nature to time itself. Gravity is the mediator between what we can perceive, measure, and infer, and what the universe truly is. Moreover, time dilation connects directly to the cosmic expansion. Light from distant galaxies is redshifted because both space and time are stretched. The universe itself ages differently at different scales. Gravity interacts with this expansion, influencing the rate at which cosmic clocks tick. The interplay between mass, energy, and space-time dynamics suggests that time is not merely a passive parameter, but an active component shaped by the universe's content and structure. Gravity's influence on time also challenges our intuitive concepts of cause and effect. If time flows differently depending on position and velocity, then the sequence of events can vary for different observers. Relativity enforces a consistent causal structure locally, but on cosmological scales, the combination of gravitational time dilation, cosmic expansion, and extreme events creates a tapestry of reality in which time is flexible and observer-dependent. In this way, gravity transcends its traditional role as a force. It is a governing principle of existence, shaping not only the positions and velocities of matter, but the rhythm and sequence of events themselves. It connects the motion of galaxies to the ticking of atomic clocks, the collapse of stars to the expansion of the cosmos, the history of the universe to the experience of the present moment. The study of gravity and time culminates in the realization that nothing in the universe is truly absolute. Mass shapes space, space-time dictates motion, gravity alters duration. The universe is not a static stage on which events unfold. It is a dynamic, interwoven fabric in which time itself is an emergent and malleable property. As we move into the next part, we will explore the unification problem, why gravity remains incompatible with quantum mechanics, the efforts to reconcile these domains, and the bold hypotheses that suggest gravity itself may be emergent, a byproduct of deeper quantum processes that govern the underlying structure of reality.
Gravity, in all its grandeur, is profoundly different from the other fundamental forces. Electromagnetism, the weak nuclear force, and the strong nuclear force are all described successfully by quantum field theories. Their interactions can be quantified, predicted, and tested with extraordinary precision. Gravity, however, stubbornly resists incorporation into this framework. Despite over a century of effort, it remains the last great holdout, the missing piece in the puzzle of fundamental physics. The challenge is that gravity is inherently geometric. In general relativity, it is not a force transmitted through space, but a manifestation of space-time curvature caused by mass and energy. Quantum mechanics, in contrast, relies on a probabilistic framework and operates in a fixed background spacetime. Attempting to quantize gravity in the same way as the electromagnetic field leads to infinities that cannot be renormalized. The two frameworks are mathematically incompatible at fundamental scales. Physicists have developed several approaches in pursuit of unification. Among them, string theory is the most ambitious. In string theory, particles are not point-like, they are tiny vibrating strings whose vibrational modes correspond to different particles. Remarkably, this framework naturally predicts a massless spin-2 particle, the graviton, the hypothetical quantum carrier of gravity. In string theory, gravity is not just compatible with quantum mechanics, it is a necessary consequence. Moreover, the theory requires additional spatial dimensions beyond the familiar three, potentially reshaping our understanding of the universe's architecture. However, string theory faces immense challenges. Its mathematical landscape is vast, possibly encompassing trillions of solutions, each describing a different possible universe. Which of these solutions corresponds to our reality is unknown. Testing the theory directly is currently beyond technological reach, as the relevant energies are far higher than those achievable in any laboratory. For now, string theory remains an elegant mathematical framework with tantalizing hints but incomplete empirical validation. An alternative approach is loop quantum gravity, which seeks to quantize space-time itself. In this framework, space is not continuous but composed of discrete quantized loops of geometry. Time, too, emerges from relationships between these loops. Loop quantum gravity replaces singularities with finite structures, potentially resolving the infinities of black holes and the Big Bang. The theory provides a mathematically consistent description of quantum spacetime, but connecting it to observable phenomena remains challenging. Unlike string theory, it does not inherently unify all forces, focusing solely on gravity. Another radical concept is the emergent gravity paradigm, which suggests that gravity may not be fundamental at all. According to this view, gravity could arise from the collective behavior of microscopic quantum degrees of freedom, a statistical effect, much like temperature emerges from molecular motion. Some versions of this idea invoke holographic principles, proposing that the information content of a volume of space is encoded on its boundary. In this scenario, gravity is not a fundamental force, but a macroscopic manifestation of deeper quantum rules. If true, it would profoundly alter our understanding of reality, transforming gravity from a force we feel into a consequence of information itself. Efforts to unify gravity with quantum mechanics also intersect with cosmology. The early universe, moments after the Big Bang, exhibited densities and energies so extreme that classical gravity fails and quantum effects dominate. Understanding this epoch requires a theory of quantum gravity. Such a theory could explain the origin of spacetime, resolve singularities, and potentially predict phenomena beyond the reach of classical physics, such as primordial gravitational waves or the formation of cosmic structures. In black holes, quantum gravity may resolve paradoxes like the loss of information. Perhaps singularities are smoothed by quantum effects, or perhaps black holes connect to other regions of spacetime through wormholes or other exotic topologies. These hypotheses remain speculative, but illustrate that gravity, at its extreme, is intimately tied to quantum processes. Despite decades of theoretical work, a complete, experimentally verified unification remains elusive. The problem is not merely technical, it is conceptual. Gravity is geometric, continuous, and universal. Quantum mechanics is discrete, probabilistic, and local. Reconciling these fundamentally different views of reality requires a profound conceptual leap, one that may require new mathematics, new physical principles, or even a radical rethinking of space, time, and matter. This quest for unification has profound philosophical implications. If gravity is emergent, if space-time itself arises from quantum information, then our familiar notions of distance, time, and causality are not fundamental. Reality as we perceive it is an emergent phenomenon, a macroscopic illusion arising from microscopic quantum interactions. The universe is more abstract, more intricate, and more astonishing than our intuition allows. Gravity, which seems so familiar, the force that anchors our feet, guides planets, and shapes galaxies, may be the tip of an iceberg. Its observable effects are vast, but its true nature may lie in the hidden quantum understructure of reality. Understanding this could reshape not only physics, but our conception of existence itself. The next part will explore the future of gravitational research, including cutting-edge experiments, space missions, and observational programs aimed at probing gravity with unprecedented precision.
From laboratory tests of quantum gravitational effects to cosmic surveys of dark matter and dark energy, we will see how humanity.
The study of gravity has always pushed the boundaries of human ingenuity, from Newton's falling apple to Einstein's bending light. Today, humanity stands on the threshold of a new era where experiments, observations, and technological advances promise to illuminate the deepest mysteries of the force that shapes the cosmos. The next decades could redefine our understanding of gravity, space-time, and the universe itself. One frontier lies in precision laboratory experiments. Physicists are measuring gravitational interactions at unprecedented scales, testing whether Newton's inverse square law holds down to millimeter or even micrometer distances. These experiments search for deviations that might reveal extra dimensions, new forces, or effects predicted by quantum gravity. Techniques range from torsion balances to atom interferometry, where clouds of ultra-cold atoms act as exquisitely sensitive probes of gravitational forces. Each experiment, no matter how small, has the potential to reveal cracks in our current understanding. Another critical arena is space-based observation. Missions like ESA's LISA, Laser Interferometer Space Antenna, planned for the 2030s, aim to detect gravitational waves with wavelengths far longer than those observable by LIGO or Virgo. By observing massive black hole mergers and potentially even signals from the early universe, LISA could reveal aspects of gravity inaccessible on Earth. In parallel, missions like the James Webb Space Telescope and upcoming observatories will map the distribution of dark matter, chart the influence of dark energy, and test gravity on cosmological scales. Space is the ultimate laboratory, free from Earth's noise and interference, where subtle gravitational phenomena can be observed directly. On the cosmic scale, astronomers are turning to gravitational lensing and galaxy surveys to probe the invisible. Large sky surveys, such as the V.C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will map billions of galaxies, tracking how their light bends under the influence of dark matter. By comparing observations with simulations, scientists can test general relativity, search for deviations on galactic and intergalactic scales, and probe the properties of the elusive dark sector. Gravity is both the guide and the signal. The shapes, motions, and alignments of galaxies encode information about unseen mass and energy. Gravitational waves will continue to revolutionize our understanding. LIGO and Virgo are now joined by Kagra in Japan, with planned next-generation detectors like the Einstein telescope and Cosmic Explorer promising even greater sensitivity. These instruments will detect fainter waves from more distant sources, capturing collisions of neutron stars, black holes, and potentially even exotic objects like boson stars or primordial black holes. By analyzing waveforms in exquisite detail, physicists hope to uncover subtle deviations from general relativity, test alternative theories of gravity, and perhaps glimpse quantum gravitational effects encoded in space-time itself. Laboratory attempts to detect quantum gravitational effects are also underway. Techniques include cooling mechanical resonators to near absolute zero, searching for minute distortions in space-time, and using entangled particles to probe gravity at microscopic scales. Though these experiments are extraordinarily challenging, they may provide the first direct evidence of gravity's quantum nature, potentially bridging the gap between general relativity and quantum mechanics. Theoretical research continues to push boundaries as well. String theory, loop quantum gravity, and emergent gravity models are producing testable predictions, guiding experimental design and informing observational campaigns. For example, certain models predict deviations in gravitational wave propagation, minute anomalies in galaxy rotation curves, or specific patterns in the cosmic microwave background. While these predictions are subtle, they offer tangible paths to unification. Gravity is no longer merely a force, it is the framework in which reality unfolds. Perhaps most audaciously, humanity may one day create artificial extreme gravitational environments. Advanced particle accelerators or engineered quantum systems might simulate conditions akin to black holes or the early universe, allowing researchers to probe the interplay of gravity and quantum mechanics in controlled settings. Though speculative, such experiments illustrate the expanding toolkit for gravitational research. From telescopes spanning billions of light years to tabletop setups smaller than a room, we are beginning to explore gravity at all scales. The stakes of this research are profound. Understanding gravity at a deeper level could uncover extra dimensions or new forces of nature, resolve the information paradox in black holes, reveal whether space-time is fundamental or emergent, explain dark matter and dark energy, provide insight into the earliest moments of the universe. In essence, gravity is the key to the cosmos. By decoding it, humanity gains access to the hidden structures of reality, from the smallest quantum fluctuations to the vast cosmic web. These endeavors also carry philosophical weight. Gravity is no longer merely a force, it is the framework in which reality unfolds. Our efforts to understand it touch upon existence itself, the origin of time, the nature of space, and the limits of knowledge. Each experiment, each observation is a dialogue with the universe, a test of our understanding against the ultimate arbiter, nature itself. The next part will examine the most profound questions gravity poses, including speculative scenarios, the ultimate fate of the universe, and how understanding gravity could reshape not only physics, but our conception of existence. Here, the known and unknown collide, revealing the limits of human comprehension and the vastness of the mysteries that remain.
Gravity is the oldest and most familiar force in our experience. We feel it every day, keeping our feet planted on Earth, guiding the moon's orbit, holding galaxies together. Yet, when we examine the universe at its smallest scales, gravity becomes the most elusive, the most resistant to understanding, and arguably the most profound puzzle in modern physics. The problem begins with the scale mismatch. Quantum mechanics governs the subatomic world, electrons, quarks, photons, everything that exists in discrete probabilistic units. These particles interact through the electromagnetic, weak and strong forces, each mediated by exchange particles, or bosons. Experiments confirm these interactions to incredible precision. The rules are clean, quantifiable, and remarkably predictive. Gravity, however, refuses to fit into this framework. Attempts to describe it as a quantum force carried by hypothetical particles called gravitons produce equations that explode into infinities when applied at small scales. Calculations become meaningless. No consistent predictive theory emerges. Unlike electromagnetism or the strong force, gravity resists quantization. It remains stubbornly classical, smooth and continuous, even at scales where discreteness dominates the universe. Consider a black hole again, but now on quantum scales. As the black hole shrinks and its mass becomes concentrated, quantum effects should dominate. In principle, the singularity should no longer be infinitely dense, but described by quantum states. Yet general relativity continues to predict an infinite curvature, while quantum mechanics requires a discrete probabilistic description of space and energy. The two frameworks are incompatible. At this junction, the intersection of the very large and the very small, physics breaks down. The tension is not merely academic, it threatens our understanding of causality and information. Classical gravity predicts that information entering a black hole is lost to the universe. Quantum theory insists that information must be preserved. If gravity cannot be quantized, or if the mechanism of information preservation is not understood, one of our most fundamental physical principles is violated. This is not a small inconsistency. It strikes at the heart of determinism and the nature of reality. One approach to resolving this tension is string theory.
Instead of treating particles as point-like, string theory models them as one-dimensional vibrating strings. These strings generate all particles, including the graviton, as vibrational modes. In theory, string theory provides a framework in which gravity is naturally quantized and compatible with the other fundamental forces. Moreover, it predicts additional spatial dimensions beyond the familiar three. However, string theory remains largely untested. Its predictions often lie at energies far beyond our current experimental reach, and its mathematical landscape is vast, perhaps even infinite, leading to what some call the landscape problem. While promising, string theory is not yet a completed solution. It suggests that gravity may emerge from a deeper, higher dimensional reality, but the experimental confirmation is still out of reach. Another promising approach is loop quantum gravity, which attempts to quantize space-time itself. In this framework, space-time is not continuous but composed of discrete loops woven into a granular structure, much like a fabric made of individual threads. These loops define the geometry of space and the flow of time, offering a picture of gravity that aligns with quantum principles. Singularities, such as those inside black holes or at the Big Bang, are replaced by finite, well-behaved structures. The infinite density disappears, replaced by a fundamentally quantum geometry. Yet, loop quantum gravity faces its own challenges. While it preserves mathematical consistency, connecting its predictions to observable phenomena remains difficult. Testing these theories requires energies or scales far beyond current technological capabilities. The universe itself becomes both the laboratory and the puzzle. The quantum gravity problem also touches the very origin of the universe. If space-time emerges from quantum rules, then the Big Bang may not have been a singularity. Instead, the universe could have bounced from a prior state or emerged from a quantum fluctuation in a larger multiverse. Time itself may be emergent, not fundamental. Causality, the chain of cause and effect, might be an approximation, valid only in the classical limit of large scales. These ideas are not mere speculation. They are grounded in precise mathematical models that extend Einstein's theory into the quantum domain. They attempt to answer questions that no classical theory can. What is the smallest possible unit of space? How does time behave near a singularity? Can gravity be a force, an emergent phenomenon, or even an illusion? Each answer reshapes our understanding of reality. Experimental hints are beginning to emerge, though slowly. Observations of the cosmic microwave background reveal fluctuations that could carry imprints of quantum gravitational effects. High-energy particle collisions may one day probe extra dimensions predicted by string theory. Gravitational waves themselves, as observed by LIGO and Virgo, may contain subtle deviations from general relativity, offering glimpses of physics beyond Einstein. Each measurement is a step toward testing the limits of our theories. The quantum gravity problem, therefore, is the ultimate frontier. It is where the macroscopic and microscopic universes collide. It is where our most successful theories, general relativity and quantum mechanics, confront each other in stark conflict. It is the place where the universe reveals both its elegance and its impenetrable mysteries. And it leaves humanity with an unsettling realization. Gravity, the force that guides our daily lives, that holds galaxies together, and that warps time itself, may be a shadow of a deeper hidden reality. The gravity we see may be only the surface of an underlying quantum structure, a whisper of a cosmic architecture far beyond our direct perception. In the next part, we will explore dark matter and dark energy, the invisible components of the universe that interact only through gravity, revealing just how much of the cosmos remains hidden and how gravity acts as our only guide in the dark.
Gravity is often thought of as a simple, predictable force, the pull that keeps us on Earth, the invisible tether of planets and stars. Yet, as we've seen, it is far more than that.
Gravity is the framework upon which reality itself is constructed. It governs space, shapes time, and orchestrates the dynamics of the cosmos. Its influence reaches from the subatomic world to the largest galactic superclusters, linking the intimate with the infinite. Consider the philosophical implications of time dilation, one of gravity's most profound effects. The passage of time is not uniform, it depends on gravitational potential. This relativity challenges our intuitive understanding of simultaneity and existence. Two observers in different gravitational fields experience time differently. Events that appear sequential to one may be nearly simultaneous to another. This is not mere abstraction, it forces us to question the nature of reality itself. If time is flexible and observer-dependent, what does that mean for our concepts of past, present, and future? Is the universe a series of events unfolding in a single shared now, or a vast tapestry of experiences, each shaped by local curvature? Gravity also informs our understanding of life and consciousness. On Earth, gravity defines the conditions for stable orbits, atmospheric retention, and planetary habitability. The delicate balance of gravitational forces governs the distribution of water, the stability of climate, and the cycles of day and night. Without gravity's precise action, life as we know it could not exist. Yet its influence is subtle. We rarely perceive how critical it is to our very existence. It is a silent architect, shaping not only the cosmos, but the conditions necessary for life to emerge and persist. The existential scope of gravity becomes even more apparent when considering cosmology. Our universe, vast and largely empty, is dominated by dark energy and dark matter. Ordinary matter, the stars, planets, and humans, is a mere 5% of the total cosmic inventory. Gravity is the tool by which we perceive this invisible majority, revealing a universe far stranger and more complex than our senses alone could detect. It connects the observable to the unobservable, the known to the unknown, allowing us to infer the existence of dark matter and measure the accelerating expansion driven by dark energy. Gravity also frames our understanding of cosmic timescales. Stars live for billions of years, galaxies evolve over hundreds of millions, and the universe itself has aged 13.8 billion years. Gravity dictates the pace and structure of these processes. It governs the collapse of gas into stars, the accretion of matter onto black holes, and the formation of planetary systems. Through gravitational interaction, the universe organizes itself into patterns that are both complex and astonishingly beautiful, revealing a deep underlying order. One of the most provocative ideas emerging from modern physics is the concept that gravity may be emergent. If gravity arises from underlying quantum processes, from entanglement or information-theoretic principles, then the fabric of reality is fundamentally different from classical intuition. What we perceive as space, time, and gravitational attraction could be a macroscopic consequence of microscopic information flow. This paradigm challenges our very perception of existence, suggesting that reality is not a fixed stage, but a dynamic, information-driven construct. Gravity also frames our cosmic perspective. It connects the fate of stars to the destiny of galaxies, and the behavior of galaxies to the evolution of the universe itself. Gravitational interactions govern collisions, mergers, and the formation of large-scale structures. The cosmic web, stretching billions of light-years, is shaped by the invisible scaffolding of dark matter, revealed through gravitational influence. In this sense, gravity acts as the invisible hand, guiding the formation and evolution of all cosmic structures. Even on human scales, gravity shapes our perception of the universe. Every telescope, satellite, and laboratory measurement relies on an understanding of gravitational effects. From predicting satellite orbits to measuring cosmic microwave background fluctuations, gravity informs our ability to probe and understand the cosmos. It is not just a cosmic force, but a methodological tool,
allowing us to infer hidden structures and unseen phenomena. Finally, gravity challenges our concepts of universality and permanence. It demonstrates that nothing is fixed. Space curves, time flows variably, and even the apparent emptiness of the universe conceals hidden mass energy. Our physical laws are not mere abstractions. They describe a dynamic, interconnected cosmos where the very fabric of reality is shaped by gravitational interactions. The universe is not static, but evolving, and gravity is the force that orchestrates this evolution. In the next part, we will explore black holes and the ultimate mysteries they harbor, diving deeper into the information paradox, singularities, and how these extreme objects challenge our understanding of physics, causality, and existence itself. Black holes are not merely astrophysical.
Black holes are the ultimate laboratories of gravity. These cosmic enigmas, predicted by general relativity, challenge our understanding of space, time, and matter. They are regions where gravity is so intense that nothing, not even light, can escape. At their core, singularities appear, points of infinite density where the known laws of physics collapse. Studying black holes allows us to explore gravity at its most extreme, revealing both its power and its mysteries. The formation of a black hole begins with stellar collapse. When massive stars exhaust their nuclear fuel, the outward pressure of fusion can no longer counteract gravitational attraction. The core collapses under its own weight, compressing matter to unimaginable densities. For stars above a certain threshold, this collapse continues until a singularity forms, surrounded by an event horizon, the boundary beyond which nothing can escape. Gravity has sculpted a region where the usual rules of space and time no longer apply, creating an arena where theory and observation collide. Observationally, black holes reveal themselves through their effects on nearby matter. Accretion disks formed by matter spiraling into the event horizon emit intense radiation as gravitational energy is converted to heat and light. These emissions allow astronomers to infer the presence, mass, and spin of black holes, even when the objects themselves are invisible. Gravitational lensing, too, betrays their influence, bending light from background stars and galaxies in ways predicted by general relativity. Through these indirect observations, black holes become accessible to human understanding, despite their hidden interiors. The most extreme manifestations are supermassive black holes, anchoring galaxies and influencing cosmic evolution. Their gravitational pull governs star formation, galactic dynamics, and the growth of galactic structures. Observations of quasars, luminous regions powered by accretion onto supermassive black holes, reveal how these objects shape the universe on enormous scales. Gravity, concentrated in these regions, orchestrates processes that affect billions of stars and dictate the behavior of entire galaxies. Yet black holes also raise profound theoretical challenges. The information paradox highlights the tension between general relativity and quantum mechanics. Classical theory predicts that information about matter falling into a black hole is lost forever. Quantum theory, however, asserts that information cannot be destroyed. Stephen Hawking's discovery of black hole radiation, now known as Hawking radiation, showed that black holes slowly evaporate, but whether the information is preserved in this process remains unresolved. This paradox strikes at the heart of physics, questioning whether the universe is fundamentally deterministic or probabilistic, and how gravity interacts with quantum principles. Gravitational waves have opened a new observational window into black hole behavior. Collisions between black holes generate ripples in space-time that travel across the cosmos, carrying information about the masses, spins, and dynamics of these extreme objects. LIGO, Virgo, and Kagra have detected dozens of such events, confirming predictions of general relativity and allowing physicists to probe gravity under unprecedented conditions.
Each detection pushes the boundaries of knowledge, providing insights into regions where direct observation is impossible. Singularities themselves remain the ultimate frontier. At the core of a black hole, density and curvature become infinite, and classical physics ceases to function. Time and space, as we understand them, break down. To describe these regions, a quantum theory of gravity is essential. Whether through string theory, loop quantum gravity, or emergent gravity frameworks, understanding singularities may reveal how space-time behaves at the Planck scale and illuminate the true nature of reality. Gravity here is not a gentle curve, but a probe into the universe's most extreme limits. Black holes also serve as cosmic laboratories for exotic physics. Hypothetical phenomena like wormholes, quantum tunneling through horizons, and the holographic principle suggest that black holes could reveal deep truths about the universe. The holographic principle, for instance, posits that all information contained within a volume of space can be encoded on its boundary. Black holes provide a testing ground for these ideas, hinting that space-time and gravity may emerge from fundamental information-theoretic principles. Moreover, black holes illustrate the interconnection of cosmic scales. A single black hole affects surrounding stars, influences galactic evolution, and contributes to the gravitational wave background of the universe. They bridge the gap between quantum mechanics and cosmology, offering a rare environment where both theories must coexist. In this sense, black holes are more than astrophysical objects. They are crucibles of reality, places where the deepest laws of nature are forged and tested. As we continue our journey, it becomes clear that black holes are not merely extreme curiosities. They are windows into the fundamental nature of gravity, the limits of space-time, and the structure of the universe itself. By studying them, humanity confronts questions about existence, information, and the ultimate fate of matter and energy. In the next part, we will examine cosmic expansion and the ultimate destiny of the universe, exploring how gravity interacts with dark energy, cosmic acceleration, and the large-scale evolution of the cosmos. We will see how gravity is not only a local phenomenon, but a cosmic architect shaping the fate of all existence.
The universe is vast, ever-expanding, and dynamic. Yet, despite its immense scale, there is an underlying force that governs its evolution, influencing the fate of galaxies, stars, and even the very fabric of space-time itself: gravity. For centuries, we thought that gravity was the force that would eventually bring the universe back together, pulling everything into a final collapse. But in the late 20th century, an astonishing discovery shattered this assumption. The universe is accelerating, not slowing down. The key to understanding this unexpected acceleration lies in dark energy, an invisible and mysterious force that counteracts gravity's pull. First observed in 1998 through the study of distant supernovae, scientists discovered that these supernovae were farther away than expected, suggesting that the expansion of the universe was speeding up. This acceleration implies that gravity, rather than slowing down cosmic expansion, is being overpowered by an unknown force. In many ways, dark energy represents a direct challenge to traditional gravitational models. Gravity, after all, is a force that pulls matter together. On cosmological scales, it governs the motions of galaxies and the clustering of matter, slowing the universe's expansion. Yet, dark energy seems to act in the opposite direction, causing the universe to expand faster as time progresses. To make matters even more perplexing, dark energy is thought to comprise about 68% of the total energy content of the universe, yet we know little about its nature. The discovery of this acceleration led scientists to propose the cosmological constant, a hypothetical form of energy that permeates all of space, causing a repulsive gravitational force that accelerates the expansion of the universe. While this idea fits with observations, it raises profound questions. What is dark energy? Why is it so weak, and why does it remain constant across the vast expanse of the cosmos? What role does it play in the ultimate fate of the universe? Gravity's role in this cosmic drama cannot be overstated. While dark energy drives the acceleration, gravity still governs the large-scale structure of the universe. On smaller scales, gravity continues to dominate, pulling matter together to form galaxies, stars, and clusters of galaxies. But on the largest scales, the interplay between gravity and dark energy determines the ultimate fate of the universe. The question is, will gravity eventually overcome dark energy, leading to a big crunch, a catastrophic collapse of the universe? Or will dark energy continue to accelerate the expansion, leading to a big rip, a scenario where the universe tears itself apart? These questions bring us to the issue of cosmic topology. The universe could be shaped in ways that defy our understanding. Is it finite or infinite? Is it flat, open, or closed? Current data suggests that the universe is flat and infinite on the largest scales. This means that as the universe expands, it will continue to do so indefinitely, with galaxies drifting farther and farther apart. Eventually, all that will remain is a dark, cold universe, with stars burning out, galaxies isolated, and the cosmos entering a state of heat death. The future of cosmic expansion is inextricably tied to the role of gravity in regulating the growth of cosmic structures. In the early universe, gravity played a key role in the formation of galaxies and large-scale structures. However, as dark energy began to dominate, gravity's influence on cosmic expansion waned. Yet, gravity still regulates the evolution of objects on smaller scales, the orbits of stars, the dynamics of black holes, and the formation of planetary systems. As dark energy continues to accelerate the universe's expansion, gravity will shape the fate of individual structures within it. One fascinating possibility is that galaxies will continue to evolve even as the larger universe stretches out of reach. Gravity will continue to bind galaxies together, allowing them to survive as isolated entities in an ever-expanding universe. But the dark energy-driven expansion will isolate these galaxies from one another. Galaxies will drift apart, eventually becoming unreachable to one another, leading to a universe filled with isolated star systems and black holes. Without cosmic mergers, without the formation of new stars, the universe could enter a dark age, where only the remnants of collapsed stars and black holes remain. This fate, the heat death of the universe, may seem bleak. However, it is also a natural outcome of the second law of thermodynamics, which states that the entropy of an isolated system tends to increase over time. In an expanding universe, the energy of stars, galaxies, and matter becomes spread out, leading to a state of maximum entropy. Eventually, the universe reaches thermodynamic equilibrium, a state where no useful work can be done. Gravity, while governing the collapse of stars and the formation of black holes, cannot reverse the overall trend towards disorder. But the fate of the universe, like the nature of gravity itself, remains full of unanswered questions. What will the ultimate state of the universe be? Will the accelerating expansion ever stop, or will it continue forever? Could new physics emerge to explain the behavior of dark energy and gravity in ways we cannot currently predict? In the next part, we will take a step back and consider the big picture of the universe's ultimate future, examining speculative theories about the universe's long-term evolution, from multiverse scenarios to the possibility of cyclical cosmologies. How might gravity and dark energy continue to evolve? What does the future hold? As we contemplate the vast scales of time and space, gravity continues to be a central actor in the unfolding drama of the universe. The interplay between gravitational attraction and dark energy-driven expansion determines not only the fate of galaxies, but also the trajectory of cosmic history on timescales unimaginable to human perception. While observations allow us to describe the universe over billions of years, speculating about its ultimate fate brings both scientific rigor and philosophical reflection into the picture. One possible scenario is the Big Freeze, or heat death. As dark energy continues to accelerate the expansion of space, galaxies drift ever farther apart. Gravity remains the local architect, holding individual galaxies and clusters together, but on the largest scales, the universe becomes increasingly empty. Stars exhaust their nuclear fuel, black holes evaporate over eons via Hawking radiation, and the cosmic microwave background cools to near absolute zero. Matter becomes diffuse, and the universe approaches a state of maximum entropy. Gravity has shaped the structure, but it cannot prevent the inevitable dispersal of energy. In this scenario, the universe becomes a cold, dark, and silent expanse, with isolated remnants of matter slowly fading into oblivion. A more dramatic alternative is the Big Rip. If the energy density of dark energy increases over time, its repulsive effect may overcome all gravitational, electromagnetic, and nuclear forces. Eventually, not only galaxies, but stars, planets, and atoms themselves would be torn apart. Gravity, normally the binding force, would be powerless against the relentless expansion. This scenario is speculative, but illustrates the delicate balance between gravity and dark energy, emphasizing that our understanding of cosmic evolution is incomplete. In such a universe, the very notion of physical stability dissolves. Gravity's role as the universal glue would be utterly overwhelmed. Another possibility, rooted in speculative physics, is the Big Crunch. In this scenario, dark energy would either weaken or reverse, allowing gravity to dominate on the largest scales. Galaxies, stars, and matter would begin to collapse back toward a common center. The universe could contract into an extremely dense state, perhaps culminating in a singularity similar to the Big Bang. This contraction could theoretically lead to a new cosmic cycle in a cyclic universe model, where expansion and contraction repeat indefinitely. Gravity in this vision is not only the force of collapse, but also the mechanism for cosmic rebirth, a sculptor of cycles beyond our current temporal horizon. Some theoretical models consider multiverse scenarios, in which our universe is one of many. In such frameworks, gravity may act differently in alternate universes or vary due to different physical constants. The ultimate fate of our universe may be part of a larger tapestry, with gravity mediating not just structure within a single cosmos, but across a vast ensemble of universes. In these models, the interplay between gravity, dark energy, and space-time could differ radically from what we observe locally, suggesting that our universe's destiny is only a fraction of a much grander, possibly infinite cosmic story. The study of gravitational interactions in extreme environments, black holes, neutron stars, and galactic collisions informs these scenarios. The insights gained from gravitational waves, cosmic surveys, and simulations of large-scale structure provide clues to how matter behaves over time under the influence of gravity. Even speculative outcomes depend on the fundamental laws of gravitation, whether as described by general relativity or by future modifications that may account for dark energy and quantum effects. In addition to cosmic-scale implications, gravity shapes localized systems over astronomical timescales. Stellar evolution, planet formation, and orbital dynamics are all determined by gravitational interactions. The distribution of mass in galaxies and clusters is a direct consequence of gravity acting over billions of years. Understanding these processes allows scientists to predict the long-term evolution of structures, from star clusters slowly evaporating to black holes merging over cosmic epochs. Gravity also has profound philosophical and existential implications when considering the ultimate future. If the universe tends toward a cold, empty state, it challenges humanity's notions of permanence and meaning. If cyclic or multiverse models are correct, our existence is a transient event in an ongoing cosmic sequence. Gravity, while a fundamental law of nature, becomes a medium through which we contemplate the impermanence, scale, and fragility of cosmic existence. Despite the grandeur of these scenarios, gravity remains a tangible tool for prediction.
By observing the motions of galaxies, the behavior of clusters, and the dynamics of cosmic expansion, scientists refine models of the universe's evolution. Theoretical predictions combined with observational data constrain the range of possible outcomes, offering insights into the cosmic future while highlighting the remaining uncertainties. Gravity is both the instrument and the limit. It allows us to probe the universe's destiny while reminding us of the boundaries of current knowledge. In the next part, we will examine the intersection of gravity and human technology, exploring how gravitational research informs space exploration, satellite navigation, planetary defense.
Gravity is not just a cosmic sculptor, it is also an engineering constraint, a practical force that shapes human technology, space exploration, and our capacity to interact with the universe. From satellite navigation to planetary defense, from interplanetary travel to the precision instruments that measure space-time itself, gravity informs both what is possible and what is profoundly challenging. One of the most ubiquitous applications of gravitational understanding is the Global Positioning System, GPS. Orbiting satellites rely on highly accurate atomic clocks, yet these clocks experience both gravitational time dilation and relativistic effects due to their motion. Clocks in satellites tick slightly faster than clocks on Earth because they are farther from the planet's gravitational pull, while their high velocities introduce additional time corrections predicted by special relativity. Without accounting for these effects, GPS positioning would drift by kilometers each day. In this way, gravity directly impacts our ability to navigate, communicate, and coordinate across the globe. Gravity also governs satellite orbits and space missions. Every launch, every trajectory calculation, every maneuver relies on understanding gravitational interactions. Interplanetary missions, such as the Voyager probes or the Mars rovers, exploit gravitational assists, the bending of a spacecraft's path around planets to reach distant targets efficiently. Gravity is not merely an obstacle to overcome, it is a tool, a cosmic lever that allows us to traverse vast distances with minimal energy expenditure. The delicate choreography of celestial mechanics enables humanity to reach the outer planets and beyond. On larger scales, gravity shapes the design of telescopes and observatories. Space-based instruments like the Hubble Space Telescope, James Webb Space Telescope, and future gravitational wave observatories must account for microgravity effects, orbital stability, and perturbations from nearby celestial bodies. Even minor deviations in gravitational pull can shift mirrors, alter focus, or disrupt sensitive measurements. Understanding and compensating for these forces is crucial to achieving the precision required to observe distant galaxies, map cosmic structures, and measure gravitational waves with extraordinary sensitivity. Gravity also informs planetary defense strategies. The potential threat of near-Earth objects, such as asteroids or comets, necessitates careful modeling of their orbits, influenced by the gravitational pull of planets, the Moon, and the Sun. Accurate predictions of orbital trajectories allow us to anticipate potential collisions, plan deflection missions, and safeguard the Earth. Gravity is both the challenge, the force dictating these trajectories, and the solution, guiding humanity in manipulating paths to prevent catastrophic impacts. Emerging technologies may even allow us to harness gravity in novel ways. Concepts like gravity assists for interstellar probes, using the sun's gravitational lens to magnify distant light, or employing artificial gravity in long-duration space habitats, illustrate the practical and imaginative applications of gravitational physics. Understanding gravity with precision is essential for the feasibility of these ventures, which may one day expand humanity's reach beyond the solar system. Gravity also underpins fundamental physics experiments. Laboratories around the world use precise measurements of gravitational interactions to probe new physics, testing Newton's law at sub-millimeter scales, searching for extra dimensions, and investigating the quantum nature of space-time. Instruments like torsion balances, atom interferometers, and superconducting gravimeters exploit gravity to reveal phenomena otherwise invisible.
Here, gravity serves as both a laboratory tool and a cosmic probe, connecting human-scale experiments to the largest structures in the universe. In the realm of space travel and colonization, gravity remains a critical consideration. Long-term human missions to Mars, lunar bases, and deep space habitats must account for the effects of reduced gravity on physiology. Microgravity leads to bone and muscle loss, cardiovascular changes, and altered sensory perception. Understanding these effects is crucial for sustaining human life beyond Earth. Artificial gravity, through rotation or other engineering solutions, may one day allow humans to thrive in environments with different gravitational conditions, further expanding our capacity to inhabit the cosmos. Gravity also shapes the frontiers of energy and propulsion research. Concepts such as gravitational slingshots, fusion propulsion, and potential manipulation of gravitational fields could revolutionize interstellar travel. While still largely speculative, these ideas rest on a deep understanding of gravitational physics, highlighting that our mastery of this fundamental force will dictate humanity's ability to explore and exploit the universe. Ultimately, gravity connects theoretical knowledge to practical application. Every technological advancement in space exploration, navigation, and fundamental physics is rooted in our understanding of gravity. From predicting planetary motion to detecting distant gravitational waves, from guiding satellites to safeguarding the Earth, gravity remains the ever-present force that both challenges and enables human ingenuity. In the next part, we will examine alternative theories of gravity, including modifications to general relativity, emergent gravity hypotheses, and their implications for both cosmology and technology. We will explore how questioning gravity's nature may open new pathways for understanding the universe and expanding human capabilities.
For over a century, Einstein's general theory of relativity has been the cornerstone of our understanding of gravity. Its predictions have been verified in countless experiments, from the precession of Mercury's orbit to the bending of starlight and the detection of gravitational waves. Yet, as profound as Einstein's framework is, it leaves unanswered questions, particularly regarding dark matter, dark energy, and the unification with quantum mechanics. These gaps have motivated scientists to explore alternative theories of gravity, testing the boundaries of our understanding and challenging what we think we know about the universe. One major class of alternatives involves modifying general relativity on large scales. The observed acceleration of the universe's expansion suggests that either a mysterious dark energy dominates the cosmos or that gravity behaves differently over vast distances. Models such as FR gravity extend Einstein's equations by including additional functions of curvature, effectively altering how space-time responds to mass energy. These modifications can mimic the effects of dark energy, potentially explaining cosmic acceleration without invoking an unknown component. However, these models must also reproduce general relativity successes on solar system scales, a delicate balancing act that often leads to stringent constraints. Another approach is MOD, modified Newtonian dynamics, proposed to address the missing mass problem in galaxies. Observations show that stars in the outskirts of galaxies rotate faster than expected based on visible matter, leading to the hypothesis of dark matter. MOD suggests that Newton's law of gravity is not exact at extremely low accelerations, effectively modifying gravity's behavior in the galactic regime. While MOD can reproduce rotation curves of many galaxies without invoking dark matter, it struggles to explain large-scale structure formation and gravitational lensing, highlighting the challenges of reconciling local modifications with the broader cosmos. A more radical perspective comes from emergent gravity, championed by researchers exploring the connections between gravity, thermodynamics, and quantum information. In these theories, gravity is not fundamental, but arises from the statistical behavior of microscopic degrees of freedom, much like temperature emerges from molecular motion. Eric Verlande's formulation suggests that the gravitational pull we attribute to dark matter could be an emergent effect of information encoded in the fabric of space-time itself.
If correct, this approach could explain both galactic dynamics and cosmic acceleration without invoking dark matter or dark energy as fundamental entities. Yet, experimental validation remains challenging, and many predictions of emergent gravity are still under scrutiny. There are also higher dimensional theories, inspired by string theory and brane world models, which suggest that our observable universe exists on a four-dimensional brane embedded in a higher dimensional space. In these scenarios, gravity can leak into extra dimensions, weakening its apparent strength on large scales and offering potential explanations for cosmic acceleration and the hierarchy problem, why gravity is so much weaker than the other fundamental forces. These models produce unique, testable predictions, including subtle deviations in gravitational waves and modifications of Newtonian dynamics at short distances, offering opportunities for experimental confirmation. Quantum gravity research provides another frontier for alternative gravitational frameworks. Loop quantum gravity, causal dynamical triangulations, and related approaches attempt to reconcile gravity with quantum mechanics by quantizing space-time itself. These models predict that at extremely small scales, space-time may be discrete rather than continuous, fundamentally altering gravitational behavior at the Planck scale. Such discretization could resolve singularities in black holes and the Big Bang, providing a unified description of gravity and quantum mechanics. The challenge lies in connecting these models to observable phenomena, as their effects are often far beyond current experimental capabilities. Alternative theories also raise profound philosophical and cosmological implications. If gravity is emergent or modified, then our understanding of dark matter, dark energy, and the large-scale structure of the universe must be re-evaluated. Are the cosmic scaffolds we observe, galaxy clusters, filaments, voids, the result of unseen matter, emergent forces, or modifications to space-time itself? Each possibility reshapes our conception of reality, revealing the fragility of assumptions and the depth of what remains unknown. Testing these theories requires ingenuity. Observations of gravitational lensing, galactic rotation curves, cosmic microwave background fluctuations, and gravitational wave signals provide avenues to distinguish between competing models. For instance, discrepancies in lensing patterns could hint at emergent gravity effects, or subtle deviations in waveforms from colliding black holes could reveal higher dimensional influences. Precision experiments on Earth and in space, such as atom interferometry, torsion balance measurements, and satellite missions, complement cosmological surveys, offering multi-scale tests of gravity's behavior. The exploration of alternative gravitational theories is not purely academic. It informs technological applications, from satellite navigation to future space missions, by refining our models of gravitational forces. It also shapes our understanding of the universe's ultimate fate, influencing predictions about cosmic acceleration, structure formation, and the interactions between dark energy, dark matter, and ordinary matter. Each refinement of our gravitational model brings both practical benefits and profound insights into the cosmos. In the next part, we will conclude by synthesizing the journey through gravity, from its observable effects on Earth to its cosmic implications, highlighting the open questions, the speculative frontiers, and the enduring mystery of the force that binds the universe together. This final part will bring together scientific understanding, philosophical reflection, and the awe-inspiring scale of the cosmos, leaving viewers with a sense of both knowledge gained and wonder yet to be explored.
Gravity is the invisible thread that weaves the cosmos together. It shapes the motion of planets, governs the evolution of stars, orchestrates the dance of galaxies, and defines the large-scale structure of the universe. From the subtle tug that anchors us to Earth to the curvature of space-time around black holes, gravity touches every aspect of reality, connecting the microcosm and the macrocosm in ways that remain deeply mysterious. Throughout this journey, we have traced the arc of human understanding, From Newton's elegant law of universal gravitation, which explained falling apples and planetary motion, to Einstein's revolutionary insight that gravity is the curvature of space-time itself. We have seen how general relativity reshaped our perception of space and time, predicting phenomena like gravitational lensing, time dilation, and gravitational waves. And yet, despite these monumental advances, gravity remains enigmatic. Its quantum nature eludes us, its relationship with dark matter and dark energy is unresolved, and its ultimate role in the universe's origin and fate remains a profound mystery. We have explored the frontiers of observation and experiment. Gravitational waves now allow us to hear cosmic collisions billions of light-years away. High-precision measurements reveal the subtleties of space-time curvature, testing general relativity to an unprecedented accuracy. Space telescopes and ground-based observatories map the distribution of dark matter and the large-scale expansion of the universe. Laboratory experiments probe gravity at millimeter and sub-millimeter scales, seeking hints of extra dimensions, new forces, or emergent phenomena. Humanity's ingenuity has transformed gravity from an invisible force to a measurable, testable, and manipulable aspect of reality. We have ventured into the realm of the extreme. Black holes, the machine's most intense gravitational laboratories, challenge our understanding of space, time, and information. Singularity and event horizon test the limits of general relativity and quantum theory, raising questions that may ultimately require a new unified theory. Gravity's role in cosmic evolution, from the formation of stars and galaxies to the expansion of the universe, demonstrates its power to shape the destiny of all that exists. Its influence extends from the birth of matter to the possible fate of the cosmos itself, whether that be a cold, dark heat death, a cataclysmic big rip, or an eternal cycle of expansion and contraction. Alternative theories of gravity remind us that science is always provisional, a quest for understanding that pushes boundaries and challenges assumptions. From modified Newtonian dynamics to emergent gravity to higher dimensional models and quantum space-time, each theory offers insights, limitations, and tantalizing possibilities. These efforts highlight the ongoing dialogue between observation, experiment, and imagination. Gravity is no longer just a force to be measured, it is a concept to be interrogated, a lens through which we explore the universe's deepest structures and the fundamental nature of reality itself. Gravity also holds profound philosophical significance. It connects our lived experience, the weight we feel underfoot, the motion of the tides, the orbit of the moon, to the grand architecture of the cosmos. It shapes time, influences the evolution of life, and links the fate of the smallest particles to the destiny of galaxies. To understand gravity is to confront the scale, complexity, and wonder of the universe, and to recognize humanity's place within it. It challenges us to think beyond intuition, to embrace abstraction, and to find meaning in patterns that span billions of light years and billions of years of cosmic history. Yet, even as we probe, measure, and theorize, gravity reminds us of how much remains unknown. Its true quantum nature, its connection to the dark components of the universe, and its role in the deepest cosmological processes are open questions. The journey of discovery is ongoing, and each experiment, each observation brings us closer while revealing new mysteries. Gravity is both familiar and alien, immediate and cosmic, comprehensible in part, but ultimately beyond full grasp, a force that inspires both knowledge and awe. As we reflect on the entirety of this exploration, one truth stands out. Gravity is more than a scientific phenomenon. It is a narrative that links the human experience to the cosmos. It is a guide to understanding the evolution of stars and galaxies, a probe into the mysteries of space-time, and a bridge connecting physics, philosophy, and existential wonder. Through gravity, we touch the fabric of the universe, perceive the flow of time, and glimpse the dynamics that have shaped existence since the dawn of the cosmos.
Gravity has taught us humility and ambition simultaneously. It demonstrates our capacity to understand, measure, and navigate the universe while reminding us of the vast unknown. It challenges our perception of space, time, and reality, demanding that we expand our intellect, imagination, and curiosity. The force that keeps us grounded also propels humanity towards the stars, towards new discoveries, and towards a deeper understanding of the universe and our place within it. In the end, gravity is both the question and the answer. It is a force, a framework, a mystery, and a guide. Its influence is eternal, shaping the cosmos from the smallest particles to the largest superclusters. Its study is unending, demanding perseverance, creativity, and wonder. And as we continue this journey, one fact remains clear. The universe is vast, its mysteries are infinite, and our exploration has only just begun.